Good afternoon, Stockholm. How are you?
Good afternoon and good morning.
Good, good. Yeah, I know you've been waiting for the breaking news, but the Duke Blue Devils won another basketball game last night. It started about, I think, 2 o'clock in the morning your time, and ended about 5 o'clock in the morning, so I'm sure you stayed up and watched it on the web. It was an exciting game. The people here in Durham are all working on their notes and homework, so is that right?
Yeah,
Right.
we guessed what the homework would be, and we started working on it.
Very good. Okay, today we want to talk about dynamics of linear systems. We had begun that conversation a few classes ago, but I wanted to finish up on that. And as our prototypical system, we're using this equation which we had considered before as part of early homework. But what I will try to convince you a little bit later is that what we do for this equation can be done for any linear system, at least of the type that we can consider an aeroelasticity. And actually, I think it's probably almost any linear system, period. Okay? So remember, alpha is the twist of this spring in our spring model. Alpha naught is some initial angle which distinguishes between the twist angle per se and the angle that the airfoil makes with respect to the float. So since we want to do a dynamic problem, we want alpha to be a function of time, alpha naught and alpha both to be a function of time. And the simplest case is simply harmonic motion in time with a single frequency omega for both alpha and alpha naught. And if we take equations 2 and put them into 1, we can solve for the amplitudes. Of course, every term goes like E omega t. And so we can compute, in particular, the ratio of alpha bar to alpha bar naught. And let's see, what is that? It's, in this case, Q over Q sub d omega alpha squared. That's from this coefficient, divided by the total coefficient of alpha over here, which will be minus omega squared. That's because of the second time derivative, plus omega alpha squared times 1 minus Q over Q sub d. Okay? And we define this to be the transfer function that transfers the amount of the input, alpha naught, to the output, alpha. So we put 2 subscripts on it to denote that, and we want to emphasize that it depends on omega. Of course, it also depends on Q over Q sub d, right? In fact, let me write this one other way, just for fun. This is a non-dimensional left-hand side, right? Well, alpha itself is non-dimensional, but even if it weren't, by the time we make a ratio, it will be non-dimensional. But the left-hand side, or excuse me, the right-hand side is also non-dimensional, but I want to make that a little more explicit by dividing the numerator and denominator by omega alpha squared, right? So we'll write this as Q over Q sub d minus omega over omega alpha quantity squared plus 1 minus Q over Q sub d. And this is just an alternative way of expressing the transfer function. Okay? So let's call this equation 3. And by the way, if we wanted to add damping in our model, we could do that, right? We could add damping up here. We could add damping down there. In fact, we may want to do that a little bit later on, but for the moment, that's not essential for what we're about to do. So With this notation and with this definition of the transfer function, we can also say alpha bar is now restoring alpha naught to the right-hand side times the transfer function. So that's all we need to say about a linear system which has a single harmonic input. But because it is a linear system, it's easy to generalize this to much more complicated motion. And the first generalization is to now, this is single harmonic motion, if you will. By that we mean, i.e., one frequency. And now we want to consider the case where alpha naught might have a lot of frequencies. And so we just allow for that by summing over some integer n, which in principle could go from minus infinity to plus infinity. In fact, we will want to look at that general case. And now we'll have alpha naught super n e to the I n omega naught t, and n is any integer minus 17, minus 16, up to plus 17. Actually goes to infinity, right? But lots of them in principle. Omega naught is usually called the fundamental frequency. And associated with that is a period, right? This is now a periodic input. It's no longer simple harmonic, but it's still periodic in time. And this is equal to 2 pi over the frequency. And this frequency, by the way, is in radians as opposed to hertz, for those of you who may want to make that distinction. Okay, well, if this is so, and so this is 5, using the concept of transfer function, from 4 and 5, we can immediately write down omega, or alpha, is equal to what? It's equal to the sum over all of these n's of alpha sub naught n times the transfer function. Now at the frequency set equal to each of these values. So if you want, you could put a superscript in here to note there are lots of transfer functions at lots of different frequencies. E to the I n omega naught t. Right? And we can easily determine what these are, what these coefficients are, if you tell me this. So there's a duality here. You tell me these coefficients, and I know alpha naught. Conversely, if you tell me alpha naught, I can determine these coefficients. In fact, the way the game is usually played is someone tells me this is a function of time, and then I find these coefficients because I want to represent this in a Fourier series, because that then immediately allows me to write down the solution for alpha. So we need to know what these coefficients are, but that's easy to do because this is a Fourier series, of course. We use orthogonality, as I mentioned the other day. We multiply by e minus I, some different integer, any different integer, 17, 236, and more generally just some other integer symbol like m, right? And therefore we perform the following operation. So consider 5 and multiply by e to the minus I m omega naught t, and integrate with respect to time over one period. The period is T naught, and you can integrate over any period you like, but for aesthetic reasons, we normally integrate from minus T naught over 2 to plus T naught over 2. It also makes the algebra a little cleaner. Okay? Now, how do I know to make this a minus sign? Well, I've done it before. That's how I know. So if I used a plus sign instead and it didn't work, then maybe I'll say, well, maybe I'll try a minus sign, right? And remember, Fourier became famous for doing this. Okay, so it may not be immediately obvious you should do that. Okay, so let's continue on to page 2 then. So we now have what? We have on both sides, we have to do this. We have minus T naught over 2 plus T naught over 2. We have alpha of T e to the minus I m omega naught T dt equals, on the right-hand side, the same integral, alpha naught, we're doing alpha naught now, super n, we can do the same thing for alpha, by the way. What? E to the I, we have a plus n and a minus m, omega naught t dt. I guess we'll call this equation 7. So we just take equation 5, multiply by this, and integrate over time. The right-hand side is 0 most of the time, pun intended. The only time it's not 0 is when n equals m. And you can, I mean, this is just a matter of looking at trigonometric functions and performing the integral. So the right-hand side is 0 if n does not equal m. And it's equal to, if n does equal m, then this factor, of course, is unity, right? This is a constant, doesn't depend on time. So when I integrate respect to time, I get a factor T naught, right? I get T naught over 2 minus T naught over 2. So I get T naught alpha naught m. By the way, there was a summation here, right? Sorry about that. That's important to recall. The point is, out of all these terms in the summation over n, the only one that survives is when n equals m. Okay? But that now, if I'm using higher mathematics, I can now solve for each of these coefficients. Each of these coefficients, taking the T naught on the other side, is 1 over T naught, this integral, from minus T naught over 2 to plus T naught over 2 of alpha naught of T e to the minus I m omega naught T dt, right? So now I have now determined these coefficients. I've determined one of them actually, but m can be any integer I like, so I've determined them all, right? So how do we play the game? You tell me alpha naught of t. I use this formula to determine the coefficients in the series, and then just remind you, I'll write equation 6 again. The response alpha of t is now summation over n of alpha naught n. The transfer function, where the frequency in the transfer function is evaluated at n times omega naught times e I n omega naught times time. Okay, you give me this, I compute this from this equation 7, and then I compute alpha, and that's all over. Okay. And this works for any periodic motion which has a certain period T naught. So this immediately allows us to go from simple harmonic motion to more general periodic motion. And now the next thing we want to do is we want to allow the period to go to infinity, because then the motion doesn't even have to be periodic. It can be any old motion we like, right? So this is periodic motion. With period T naught. Now we'll do what, if we will, we'll do non-periodic motion. Or arbitrary motion. By letting T naught approaches infinity. Now it turns out we have to be careful how we let that approach to a limit take place, but again, it's been done before, so we probably can do it again. And again, you might or might not decide to do the limit quite the way that Fourier determined, but eventually, sooner or later, someone else would have found that out. Yeah.
In terms of the orthogonality, so can you just remind me what are the requirements for orthogonality? When can we say that this is 0 when n is not equal to n?
It depends on these functions. Think of it this way. Remember when we were looking at mode shapes back in the day, we were talking about orthogonality with respect to spatial variables, right? We had some variables like psi n of x times psi m of x dx, and we said there are some functions where that's 0 if m does not equal n, right? We said that. In this case, it's orthogonality with respect to some functions of time. So in this case, if you will, if psi n of t, psi m of t dt is 0 if m does not equal n. And in particular, we're looking at what kind of a psi n are we looking at? We're looking at e I n omega naught t, and what's psi m? It's e minus I m omega naught t. I mean, a lot of functions aren't orthogonal. In fact, the functions that are orthogonal are a small but very important subset of all functions in the world, right? So you have to prove orthogonality for the functions in hand. So the only way you really know this is true is to perform that integral. You take these functions, e plus and minus I n or m omega naught t, and integrate from minus t naught over 2 to plus t naught over 2 and see if in fact they're orthogonal. Okay. And they will be or they will not be, as the case may be. And by the way, orthogonality also depends on the interval. If I integrated not from minus t naught over 2 to plus t naught over 2, but I only integrated from 0 to t naught over 2, for example, these things aren't orthogonal over that interval of time. So there are two. One, it depends on the functions, and the other, it depends on the interval of interest. Okay. So not all functions are orthogonal. Not all classes of functions are orthogonal. But these are, thank goodness. Right? These are, thank goodness. Okay, and that's a big help. So in fact, I guess I'll assign that as the first part of the homework problem. It shouldn't take too long. You should prove that this orthogonality condition holds, right? But you can integrate exponentials, I hope. I think you can do that. Okay. So what do we want to do next? Well, what we want to do is we want to take the limit of equations 5, 6, and 7 as t naught goes to infinity. Before I do that, let's see if there are other questions. Other questions here in Durham? No? Stockholm, do you have any questions? We're about to take this limit, but before we do that, any questions from Stockholm? And Wall falling asleep.
There's no questions from him.
No question.
No questions, good. All right, so let me write these equations down again. And so we'll have them in front of us. We have what? Alpha naught is this summation, alpha naught n e I n omega naught t. That's equation 5. 6, again, is alpha and I'll make this explicit since that'll be important. And 7 was what? 1 over T naught and well minus T naught over 2. Minus n. How about that? That would be better, right? For those of you paying close attention, when I wrote this before, I had an M here rather than N. Does it matter? No, it doesn't matter. Sometimes I have to be, if I'm playing around with two different integers, I need to probably call them by two different symbols. But if I only have one integer in any given equation, I can use whatever integer I like. Last time I liked M, now I like N. I could use something else. Okay. So let's now take the limit as T naught goes to infinity. If I look at 7 and let T naught go to infinity, what do I get for this? This is a trick question. 0. That's not what I want to do then. On the other hand, if I took the T naught up here and had this product of T naught times this, I took the limit, that'd be perfectly nice. I mean, my limits would just go to infinity, right? But this is hopefully a well-behaved function. That's okay. So that's a clue. Presumably that was a clue to Fourier. But the way he looked at it, and the way people in the modern era explain this is as follows. First of all, I have an integral here, right? I have a sum up here. I really want to convert that sum to an integral. Now, you may not know that that's what I want to do. You may not know that that's what you want to do. But if you'll let me pursue that path for a moment, you'll see that that is, in fact, what you want to do. Okay. But now let's think that not only of this period of getting large, but let's also look at the frequency. Remember, it's defined as that. What happens to omega naught as T naught gets large? It goes to 0. But now let's do something else. Let's define delta omega. Delta omega is an increment in omega. Remember, there are lots of omegas. There's 1 times omega naught, 2 times omega naught, 17 times omega naught, also minus 17. There are lots of them. There are an infinite number of these, right? How far apart are any two adjacent ones? Well, it's using higher mathematics. It's n plus 1 omega naught. That's the n plus 1 frequency. Minus the one previous. That's n omega naught. Using higher mathematics, it's omega naught. So when omega naught goes to 0, the frequency interval between two adjacent frequencies is getting smaller and smaller. That means in this limit, the entire frequency spectrum is continuous. It's no longer discrete in this limit, right? That's why this sum is going to become an integral. So let's look at now, consider 5 again. And I'm going to do the following. I'm going to write alpha of t, alpha not of t, equals this summation. And I'm going to have alpha naught over n. I'm going to divide by delta omega, which in fact is just omega naught, right? And then I'm going to have e to the I n omega naught t times delta omega, right? And now if I pretend like this is some finite quantity, which it will prove to be, then this summation over n in the limit n times omega naught is not 0, it's finite, because remember n is going to go off to infinity. And there are a lot of them. So this becomes an integral over frequency of this thing, thank you, of this thing, which I'm now going to define as suggestively of a star, which now becomes a continuous function of frequency. E to the I, n times omega naught is just omega, t, d omega. So that's the limit of equation 5, as t naught becomes large and omega naught tends to 0. But now let's look at equation 7.
Will it be alpha naught star n?
Where is it?
This will be some different coefficient of this thing.
Yeah, the coefficient has gone away, right? Because I'm thinking alpha naught, because when I do the summation, I'm summing lots of terms, right? But the terms get progressively closer together in the frequency spectrum, so the summation becomes an integral. This is really the classical definition of what an integral is. And if you go back to the calculus, you define integrals as infinite sums, as the increment in the sum gets smaller and smaller. The increment along some variable. In this case, it's the frequency spectrum. Right? So, okay, so let's now look at 7. If I look at 7, I really know that I want to multiply by t naught to get something finite. But another way to think about it is I'll do the same thing here that I did down here. I'm going to divide by delta omega, right? Since that proved to be useful for this purpose. So when I get to 7, I'm going to take 7, divide by delta omega. And now I have 1 over delta omega times t naught times this integral. And now in the limit, this is going to become just a continuous frequency. Thank you. But what is this? Well, delta omega is omega naught, but omega naught is 2 pi over t naught. And so delta omega times t naught is just 2 pi, right? So this just becomes 1 over 2 pi, which is a nice finite quantity. You see, by making this definition, not only did I help myself here, but when I get down to here, I get something on the left-hand side that's finite. I call this alpha star. Again. So, this is the limit of 5, and this is the limit of 7. And together, these are a pair of equations. They're a Fourier transform pair, okay? This equation says, if I know this function of time, and of course, these limits now go from minus infinity to plus infinity. If I have this function of time, I multiply by e minus I omega t and integrate over time, and I produce something called alpha star. That is the Fourier transform of this function of time. Conversely, if you give me a Fourier transform, then I put it in here, and I multiply by e to the plus I omega t, right? There's a minus here, plus here, and integrate over frequencies, and that produces a function of time. Why is that useful? Because I know how to relate what's happening in the frequency domain for a single frequency, right, using the concept of a transfer function. So if I want to now look at equation 6, what I'm going to do here is I'm going to divide by delta omega and multiply by delta omega, and this sum is going to become an integral, right? So the limit of 6 then the limit of 6 then is alpha of t equals the integral from minus infinity to plus infinity is also 1 over 2 pi of alpha star of omega e to the I omega t. Oops, I had to put the transfer function in. That's important. Transfer function from alpha naught to alpha of frequency. E to the I omega t d omega. Right? This is an integral over frequency. Okay. Okay. So the way the game then is played is I use equation 7 to find alpha star, right? Knowing alpha of t, I use equation 7 to find alpha star. I multiply by the transfer function, multiply by e I omega t, and do this integral frequency, and then I'm done. So the key is knowing the relationship between the input and output for a single frequency. Once I can do that, once I have that, then I can do an integral, and I have the response at any time for any input. Of course, I do have to find the Fourier transform of the input of alpha naught. I see some perplexed and frowning faces in Durham. There are probably similar faces in Stockholm, which I can't see as readily. So let me pause, because I'm about to do something else. And before I do something else, I want to make sure we're okay so far. I have summations over discrete frequencies, but I want the interval between those frequencies that become progressively small, which corresponds to the period in time becoming progressively longer. And if I'm careful about how I take that limit, those summations become intervals, and I go from Fourier series to Fourier intervals, or Fourier transforms. I'm waiting for protests, questions. Not yet? All right. We're going to press even further then. Okay, this is the limit of 6. Let me remind you of what 7 was. This was alpha star of omega is equal to 1 over 2 pi integral from minus infinity to plus infinity of alpha of t e to the minus I omega t dt. Okay? So again, here's the way the game is played. You tell me, excuse me, this is alpha naught. Well, it's true also for alpha, as it turns out, but in particular, I wrote it down for alpha naught. You tell me alpha naught now, some arbitrary function of time. Doesn't have to be periodic in time. It can be any function of time. I perform this operation and I produce alpha star, which is this Fourier transform. Take that plus the transfer function, perform this integral, and I get alpha of t, the output, right? But I could do another thing, which may not seem like a good idea if you haven't seen this before, but it is a really good idea. I can take this alpha star and put it in here and get something that's really interesting. Trust me. But when I do that, I have to be a little careful because why? Here I'm using t. It's a integral over time, and what appears on the left-hand side is really just a function of frequency. And on the end up here, I have another t, which is the time at which I want to know alpha. So to avoid confusion, of course, you would never become confused by this, but to avoid confusion, I'm now going to change the symbol for t here, so I will distinguish between the time that appears in this equation and the time that appears in this equation. There's no harm in doing that. In fact, there's a lot of good that comes from doing that. If you don't believe me, you can try it the other way and see if you manage to keep it all straight. Okay, so I'm going to now take this equation and place it in this equation, and now I will have a double integral, right? I have alpha of t equals 1 over 2 pi, the integral from I think yeah, I did. I told you something was wrong. Let me go back. Yeah, there's no 2 pi here. Sorry about that. Right. Let me go back. Here's equation 6. I'm going to multiply and divide by delta omega, right? And this summation over frequency will become an integral. But there's no 2 pi here. I just got excited for the 2 pi there. Sorry about that. Sorry about that. Okay. So I don't need this 2 pi here yet. There's going to be a 2 pi from here, but not. I was going to end up with more 2 pi's than I wanted, or you want, for that matter. Okay. So equation 6 now is the integral from minus infinity to infinity of alpha star, but alpha star is 1 over 2 pi, the integral from minus infinity to infinity of alpha naught of t, e to the minus I omega. Oh, I had to make this a tau also, right? Alpha of tau, e minus I omega tau, d tau. That's just alpha star, right? That appears here. Times h of alpha naught of omega, e to the plus I omega t, the omega. Right? But now, what I want to do is I want to interchange the order of the integral over omega and the integral over tau. Again, you might or might not think to do this the first time you are playing it with it, but that turns out to be a reasonable thing and a useful thing to do. So, and since the integrals are from minus to plus infinity, I don't have to worry about the limits. If the limits were finite, I have to worry about the actual area, but I'm integrating over everything, right? So I don't need to worry about the limits. So then I'm going to end up with the following. The outside integral is over tau. Again, it's from minus infinity to plus infinity. I'll take alpha naught of tau outside. And then inside, there's going to be the integral over frequency. And that will be h alpha naught of omega e to the I omega. There's a plus t and a minus tau, so that's t minus tau, the omega. And there's also a 2 pi, and I have I'm going to put the 2 pi there. Okay. And what is this thing? I'm glad you asked. What's this thing that's integral over omega? Well, the first thing you note about it is it has nothing to do with the input. It only has to do with the dynamics of the system. It only has to do with the transfer function. And in a linear system, the transfer function itself doesn't depend on the input. That's the nature of a linear system. If for a nonlinear system, it might. Okay, but for a linear system, it doesn't. So I'm going to define I alpha naught, a function of t minus tau, because this integral, once I perform the integral over frequency, minus infinity to plus infinity, once I perform this integral over frequency, I just have a function of t minus tau, right? So I'm going to define 1 over 2 pi, the integral from minus infinity to plus infinity of h alpha naught omega e, thank you, e minus I omega t minus tau d omega as some function of t minus tau. And we'll talk about what that function means in a moment. Okay, so this is a definition. I guess I should give this I'll call this equation 8. This is a definition. Now, using this definition, I can write the previous equation for alpha t more compactly. It's just the integral from minus infinity to plus infinity of alpha naught of t I alpha naught of t minus tau d tau. The advantage of this is once I know this function I, which doesn't depend on the input, then I really know the output for any input at time, any kind of input and its time dependence, if I can perform this integral.
You can pay the exponential term. This should be positive. The exponential term.
You're talking about this equation?
8.
8. Yeah. What are we?
The exponential part. That.
Is it positive? Oh, you're right. Thank you.
Extra credit.
That would help. Thank you. Yes, you're right. Absolutely. Thank you. Okay. Okay. Now, how do I determine this function, I? I can do it several ways. If I know the transfer function and I can perform this integral, I can determine I. I'm going to let you do that for this example. Okay. There's another way of determining it. If somehow someone gives me a computer code and it's a black box, I don't know what's inside of it, but it was given to me by a trustworthy source. Or you could also think of someone giving me an analog computer, otherwise known as a physical experiment, where in this physical experiment, it could be wind tunnel model, I could give my wind tunnel model a certain alpha naught of tau, and then I could measure the response. Then I could determine this function. How would I do that? Well, there's a very special kind of input which will give me this function by measuring the output. Big if I select alpha of tau to be a delta function, this is not the virtual change in anything. This is a real delta function, right? What's a real delta function? Well, if I plot delta versus tau, it's a function of time, right? It's a function which is zero almost everywhere, except over a small interval of tau, which I'll call epsilon, and whose value, whose height, if you will, is 1 over epsilon, such that the area under this curve is 1, right? It's 1 over epsilon times epsilon. But I'm always thinking of epsilon as being small and letting epsilon tend to 0. When epsilon tends to 0, the width of this becomes very small, but the height becomes very large. But the area under the curve is always 1. Well, if I make this a delta function and I integrate over all time, tau, the only thing that will survive if I put a delta function here is this function evaluated when tau equals 0, right? So if this is true, then alpha of t for this very special alpha naught of tau is just equal to I alpha naught of t. So if I can put a delta function into my computer code, or I can put a delta function into my physical model and I measure the response, I have this impulse function directly. And that's one reason why this is useful. People actually do try to measure impulse functions from physical experiments. They're assuming that the system is linear. That's the big assumption. But if you want to know the impulse function from an experiment, this equation tells you how you go about finding it. Okay. I think that's all I want to tell you about that. So again, I'm going to pause, but I'm going to start writing down some homework. Let's see. What were we going to do as homework? Oh, I know. You were going to
Watch the next basketball game.
well, that's very important. That's very important. When is the next Duke basketball game?
Saturday.
What time? Who are we playing? Home or away? Very good. All right. Well, you got that part of the homework. I'm going to give you a perfect 10 on that part of the homework. Okay. I'm going to, first of all, go back here. Remember the equation we had to start? Got to give you something to do, though. Interesting. Okay. From this, you can find the transfer function, right? But I want you to find the transfer function for a slightly more complicated case. Let's put in some damping. Okay, so find h sub alpha naught of omega. Find I alpha naught of t, or t minus tau. Seems like there's one other thing I wanted you to do. What else? Whoops. Oh, you were going to prove what I was talking about. Thank you. Very good. I'm glad you remember. You're going to prove that I m n minus n or n minus m doesn't matter. N minus m omega naught t dt is 0 for m not equal to n.
Should that upper bound not over 2?
I'm sorry?
Should that upper bound be T not over 2?
Oh, I surely should. Thank you. Yeah, that would. In fact, without the over 2 is not true.
And for the equation,
that was a trick question. Yes, what?
For the equation with 17, the alpha is usually like, and
Yeah.
right hand side is the alpha.
Oh, I always leave that out, don't I? Why do I always leave that out? I have a.
And then on the right hand side is alpha not.
There's alpha now. Thank you. Yes. Yeah, that would help. That would definitely help. Yeah. Okay. I'm gonna give you some. This is not very challenging. You can do this while you're watching the basketball game. So what else could you do that would be more challenging?
Choose the best play of the basketball game.
Well, I can do that. Why don't we put a nonlinear term in? Because then you'll see you'll get in trouble. Okay. So for extra credit or whatever. So add. Let's see. Let's add another term, which will be nonlinear effects. Alpha double dot plus 2 zeta alpha omega alpha alpha dot plus omega alpha squared 1 minus q over qd times alpha, and let's just put in a alpha cubed term. Why not? In fact, I guess we should make it dimensionally consistent. So we need plus omega alpha squared times alpha cubed, right? Equals omega alpha squared. Okay, so see if you can make it work for this case. You can, but you're going to have to make some additional assumptions and approximations, and so what happens when you do that, right? Okay. Now that's still not very challenging, but if you're going to watch the game, I'm going to give you credit for that. So, okay. Any questions about the homework?
You want us to find the same things for that nonlinear term?
Say again.
The last part, what do you want us to do with it?
See if you can generalize this theory to this case. I mean, in this, let's see. I guess in the first case, in all these cases, we should give you some alpha naught. Given what alpha naught do you like? Given alpha 2, find out. What type of alpha naught would you like?
Specifically the constant 0.
No. Let's see. Alpha naught is e to the minus what? Minus, we don't want to make it too, well, yeah. Minus omega alpha t cosine, no, we won't do that. Let's do two e minus zeta omega t cosine omega t. How's that? And you can non-dimensionalize this if you want to. So if you want to, you can non-dimensionalize. Zeta is going to be non-dimensional. You can non-dimensionalize the omega by omega alpha. But let's, certain values of omega. Let's see, omega equals omega alpha would be a good, interesting case, right? But you also might try half of that and twice that. Right.
Zeta is the same as the delta.
Say again?
Zeta is the same as the.
Well, this is not this damp. This is the physical damping in the model, but this is just a decay constant that says how the input is decaying with time. If zeta said equals 0, then this is just oscillating with a certain frequency forever, right? In which case, since it's periodic in time, you don't need the Fourier integral, right? You could just use the Fourier series. So I'm going to introduce it. I want this to be a transient because otherwise it's periodic in time. I don't want to be periodic in time because then you don't need all the apparatus of Fourier transforms and Fourier integrals. Okay, one other thing, and for this particular case, you can actually find an analytical expression for I. But in more general cases, particularly if you had a physical system and you were doing an experiment, you might measure the transfer function, right? You put inputs in at various frequencies and measure the transfer function. And then you might have to, given the transfer function, find I by numerically integrating that integral. Remember what I is? I can find it again. I'm going to leave all the subscripts off. It's 1 over 2 pi, the integral of the transfer function, right? Just oops. Thank you. E, this is a function of time. E I omega t d omega. So in your homework, you will be able to find an analytical expression. But why don't you do it numerically as well? That is, this is just a quadrature, right? You can call MATLAB and given this, and tell MATLAB to do this integral for you numerically. And when you do that, you might want to non-dimensionalize it so the frequencies are non-dimensionalized by omega alpha, right? And you probably are not going to integrate out to infinity, either plus or minus, right? You're going to have to decide how far out you integrate before you stop. Also, h of omega is a complex number. This is clearly a complex number, right? I do this integral, this better be a real number, which means that the imaginary part of this integral should turn out to be 0. In a numerical calculation, it won't be exactly 0, right? Because there's always some round off there. But the imaginary part should be a lot smaller than the real part. But that would be interesting for you to see. So do this analytically and compare to a numerical result. And if you normalize all the omegas by omega alpha, that will correspond to normalizing t by multiplying by omega alpha, as you'll see. So if you normalize things this way, then it's universal. You don't have to even pick omega alpha, right? Okay. Now there's one more thing I want to tell you, and I have 5 minutes. That's more than enough time. But are there questions before I tell you the punchline, as it were, on this story? Stockholm, how about you?
We're good.
Okay. The most general form, at least for aeroelasticity and for lots of other systems as well, the most general form of the equation of motion looks just like the equation we were describing. And let me write it down for you. It's m sub m times q sub m double dot. Does that look familiar? Plus 2 zeta sub m omega sub m q m dot plus omega m squared q sub m equals capital Q sub m. Where Q sub m, small and large, are both functions of time. W, the displacement of a wing, for example, which might depend on x, y, and time, can be expressed as a series of functions of time times functions of space. Those are the natural modes that your finite element code is going to give you. M sub m is the double integral over space of the mass per unit area, which might depend on x and y, times the mode shape squared. The omega sub m are the natural frequencies of the structural modes. What else? Oh, zeta m, of course, are the modal damping coefficients. Which come from where?
Experience.
Experience. Possibly an experiment. Although even an experiment, you're probably only going to determine, if you have 17 modes, you're lucky to know 2 or 3 damping coefficients. And you make a wild guess, well, not wholly, an educated guess, how about that? About the other 14. And Q sub m will be, thank you, the integral of the pressure, the force per unit area acting on my structure, times the relevant mode shape, dx dy. And how many of these equations do I have? Well, 17 modes. It would not be unusual to have 50 or 100. Often in preliminary design work, you might have less than 10, since you don't know enough about the airplane yet to justify using 100. But as the design moves along and the test program moves along, and you have a better and better definition of the structure, you try to find more and more modes. But the point is that these equations, even though there may be a lot of them now, look just like the one we dealt with before. And all those things we said about the particular example today applies. Again, you know, I find the transfer function, right? I can find the impulse function. Therefore, I have the input-output relationships and away I go. Now, there is one, in aeroelasticity, there is one major challenge, and that is we haven't spoken much about how you determine the pressure. That's aerodynamic theory. So we're going to start talking about aerodynamic theory really soon. And that will prove to be an interesting topic. So we've now covered dynamics of linear systems. I think we spent 2 lectures, maybe 3 at most. Again, we went through it fairly quickly because this could be the subject of an entire semester. We have not spent quite that much time on it. So if you've not seen this before and you have questions, it's okay. We did this fairly quickly. But I think what we have discussed gets the essence of the subject, and I think it's the most compact way of understanding it and hopefully retaining it. Okay. Questions? Yes, good point. Yes, we should talk about power spectrum. We will talk about that, power spectrum. Yeah, before we go on to unstandard dynamics, we should talk about power spectrum. Yeah. For those of you who don't know what that term is about, there is based on what we've already discussed, there is a theory that's very compact and very useful for treating random inputs and random outputs. Strictly speaking, you don't need it. I mean, if I want to know the random response of the system, you give me alpha naught as a random function of time. They're random number generators, so we could take it from experiment or whatever. And then using what we already know, we could compute the time history of the response, right? Because a random input is just, in some sense, a special case of a arbitrary time dependence. But often, for random motions, you only want to do two things. One is you want to know the average value of the time response, and you want to know the fluctuations about that as represented by the root mean square deviation from the mean response. And if that's all you want to know, and often your knowledge of the input is such that that's all you're really justifying knowing, right? You don't know, that's probably about all you know about the input too. Then there's a very nice theory based on Fourier transforms that gives you an input-output relationship that is quite compact. So we will talk about that. Thank you for reminding me. And that's also in chapter 3. It's right after the material we've just been discussing. Yeah. So I will definitely give you that. Any other questions? Yes, sir.
The question is a matter of definitions. Is the difference between harmonic and periodic?
Yes.
What is it?
Harmonic means there's a single frequency. So let me draw a picture. Maybe that will help. Simple harmonic means that if I draw, thank you. It's just, I don't draw the sinusoid very well, but this is my approximation of sinusoid. It means it's just a nice single sinusoid. And mathematically, that's E represented by E I omega t. Okay? So it's a sine or a cosine. It's a combination of sines and cosine. Periodic means so there's a period here, right? So let's assume that I'm still dealing with the same period, but the function isn't necessarily a single sinusoid. It could be I gotta go the other way. How about that? Well, let me draw something that's easier to draw. So here's a half a period. So it's a constant over one half of the period, and some different constant over the other half, and then goes. So this is periodic, right? And you can represent this so-called square wave as a Fourier series. That is, it can be lots of these added together. But it could be some more general function of time, but it has to repeat. So anything that repeats is periodic, okay? But not everything that repeats is subharmonic. Does that help? Yeah. Okay. Other questions? Any more questions from Stockholm?
No questions.
Thank you. We'll see you. Oh, on Tuesday, I'm going to be in Washington, D.C. And so, you want to take over the class? No. we will have a break. We'll have a break on Tuesday. You'll be working hard on your homework, right? So we will next meet a week from today. Yeah.